Okay, let's start. So last time I talked about control of manipulators. This is probably going to be the last part of this course. Uh, this is from the last time. That's the equation of a manipulator. There's a mass times the acceleration. C is the Coriolis force, also the centripetal force, and G is the terms due to gravity. That all equals the torque, and these are all matrices, right? Depending on the number of links. For example, for a 6-link manipulator, M would be 6 by 6, Q would be 6 by 1, and so on. So, in order to look at control of a more complex thing, let's look at something which is much simpler, which is reduce this equation to a scalar equation. So we have a mass, like a number, so a scalar, a damping term, CQ dot, and then a spring-like term. So this is an equation of a spring mass damper. If you put torque equal to 0, in this case it's really not a torque, but it's a force. So it's basically a spring, a damper, and there's a mass. And so if you pull this mass and then release it, then because of the spring, it's going to go back and forth. But because of the damping, it's eventually going to come back to the 0 state. So what you can do is you can rewrite the equation in this form, and this equation comes from vibration, where you have a damping term and the natural frequency, the well-studied system. Depending on the damping ratio, we get three types of responses. We have overdamped. Okay. The deviation, which is this, dies down and takes a while to die out. The underdamped case is when there's an oscillation, so it goes back and forth from positive Q to negative Q and eventually dies out. So it's going to wobble and then die out. And then there's a critical damping case where you get from the perturbation to 0 in the shortest possible time. And you, as a control engineer, you want to make the system be critically damped because it doesn't have overshoot. It takes the shortest time to damp out. So you are looking to make the system critically damped. That's what you're after. Okay, so our system, which has a certain mass, damping, and spring term, by itself will not be critically damped, but because you have full control, you can apply whatever force you want. You can actually make it whatever you want. You can make it. You can take an underdamped system, make it overdamped, and so on. So in this case, we're particularly interested in making the system critically damped because that gives no overshoot and fastest response. And so what we do is I wrote down the torque as what is known as a proportional derivative control. Proportional derivative control. It's called proportional and derivative control because there's a constant which multiplies with sort of like a proportional term. Q is the angle and the set point in this case is 0. So Q minus 0, that's the proportional part. And then it's a function of the velocity, so that's the derivative part. So it's a PD controller, a proportional derivative controller. We sub that inside the equation of the spring mass damper. We rearrange terms to get this equation. So now you can see that the damping, the natural frequency is the same thing as before, but you have a KD term appearing for Kp appearing for natural frequency, and for damping there's a Kd, and Kp and Kd is something which you can choose because you have full control on the system. So now you can tailor the natural frequency because you can change Kp. You can tailor the damping because you can find Kd. So what we did was I ended up setting the equation for critical damping, which is this. The damping equals 1. I solved for Kd. So I got, because it's a quadratic equation, I got 2 roots. Plus or minus. I ignore the negative one because the damping has to be positive. So there's only one root which is of physical meaning, physical any value. But this Kd is a function of Kp, and Kp you can choose. So it's really, you fix a Kp, and this equation gives you Kd, and so that system will be critically damped. right? So this is the equation for KD as a function of KP. That's the equation you'll use. And in my simulation, which I shared last class, I showed you that as you increase KP, KD is adjusted according to this equation, and the response gets faster and faster. And you cannot go to a very high KP because your system will get unstable. So if you try to do PD control for your car, for your line following, if you just keep increasing your KP, it'll actually start wobbling back and forth, crazy, because in reality there's noise, and when you multiply KP with Q, Q is noisy, then you're going to amplify noise. So that's what happened when you also did the simulation for a car tracking the curve. You had I think it was a proportional controller, and you increase the KP, you see, so, and when there was noise, you saw that it went unstable. Normally it would not go unstable if there was no noise. So today's, I'm going to increase the system complexity, but before that, you can actually represent the system using a block diagram, and block diagrams are important because people who are control engineers like to talk in terms of block diagram. Okay, so block diagram is a pictorial representation of the control system. So the system here was MQ double dot plus CQ dot plus KQ equals torque, or let's keep it a torque. So the block diagram for this, and I'm pretty sure this is very self-explanatory, plus KQ. So that's the system. So that's your physical model containing the spin mass damper. There are sensors which give you Q. An encoder would give you Q for a rotary joint, and Q dot. And this information goes to your controller, which in this case is KP for Q. So KP, KD for Q dot. So what this block does is it takes Q dot and Q, and then the output is KD times Q dot. The output is KP times Q. And since we're going to sum this up, goes to this block. This block is used to sum. In this case, it's negative feedback, so I put a negative sign, and that goes back to the input. This is basically torque. So the torque here is the sum, but it's really negative. So it's negative KD Q dot, which is this, and negative KPQ, which comes from here. So that's a block diagram, and people like to use these to talk about designing control systems. If you're writing that equation, this conveys more information. Because it just tells you, it conveys more information. Well, not really in this particular case, but sometimes you put sensors, you show what sensors are there and what are measured and so on. So it conveys more information in that sense. So for example, sometimes you do not have access to a sensor which gives Q dot velocity, and you're going to take Q and then numerically differentiate it, and that can be shown on the block diagram, and you cannot show that using that equation. You'll have to do some more writing. Okay, so the block diagrams are important. Let's move to a slightly more complex system. We talked about single degree of freedom system, a single spring mass damper, and I showed you that you can control the system by assuming torque equals a PD controller, and then figuring out what you can put for the damping term KD as a function of KP to achieve critical damping. Now let's take a more complex system. So Now consider a 2DOF system. Okay, eventually we should be able to control n degree of freedom system. So let's look at a 2DOF system. So again, equations are m. The same equation holds true, except that now you'll have a little bit more complexity. Plus CQ dot plus KQ equals tau. So what really M would look like would be M11, M12, M21, M22, Q1 double dot, Q2 double dot, plus C11, C12, C21, C22, plus K11, K12, and so on. This is what a 2 degree of freedom spring mass damper system would look like. So most times some of those masses and damping terms are zero, but this is how a generic 2 degree of freedom system would look. And so now if I ask you, can you take what we did for 1 degree of freedom, 1 degree of freedom system and generalize it to 2 degrees of freedom? Well, you say torque equals, as I wrote down earlier, Kp Q minus Kd Q dot. What does this look like? Well, it will look like this. Minus Kp11, Kp12, Kp21, Kp22, Q1, Q2 minus Kd11, Kd1, Kd12, Kd21, Kd22, Q1 dot, Q2 dot. Okay, so for a 1 degree of freedom system, we have to only choose Kp and Kd, two numbers, right? And we wrote Kd as a function of Kp using critical damping. Now we have not two numbers, but we have 8 numbers. 4 here, 4 here, 4 gains, 4 Kds, and that's just, you'll have two constraints posed by critical damping. And so to take the system, write the critical damping ratio, and figure out Kp and Kd is a long process. It's doable, but it's much harder. Okay, so we can find Kp and Kds such that the system is critically damped, but the calculations are too long. And complicated. So it's pretty complex to do that, and nobody actually does that. Nobody tries to find a controller of this complexity. Nobody tries to find 8 numbers for a 2 degree of freedom system. So it would be nice if we reduce this to be, instead of doing design of 4 numbers, 8 numbers, you just design 2 numbers, this and this, that and this. So if you can get rid of these two, that would be nice. And so here's the trick: how to reduce this from 8 to 4. And then you can think of 2 systems, each of, so then it'll be, once I reduce it from 8 numbers to just 2 numbers, sorry, 4 numbers to 2 numbers, and 4 numbers to numbers, we'll be designing the first system separately from the second system. So it's like, think of breaking down a 2 degree of freedom as two separate 1 degree of freedom systems. And once you do that breaking down, then it's like designing two separate controllers using the formulas for a 1 degree of freedom system I talked about. So this is going to make our life much easy. So what I said might be too hard to understand. When I put the equations down, it might be much easier. So here's the idea. It's called control law partitioning. So maybe before that, we will reduce the system complexity first, and then design two independent one single degree of freedom controllers. Okay, what that means is torque 1 will be minus k p1 q minus q1 minus k d1 q1 dot, and tau 2 will be minus kp2 q2 minus kd2 q2 dot. So it's going to reduce to just 4 numbers, and those are simple equations which we've seen for a single degree of freedom system. So this method is called control partitioning. Okay, and I'm going to show you how it makes the life simple. So the system dynamics is mq double dot plus cq dot plus gq equals torque. Okay, what we do is we choose a controller of this form. Torque equals m hat, and I'll tell you what m hat is, minus kpq minus kdq dot plus c hat q dot plus g hat q. Okay, so m hat c hat g hat are estimates of mass g, c and q, c and g. So why are they estimates? Well, when you have a manipulator, you do not know the mass, and so you have to do some system identification to figure out the mass. For example, the mass for a mass, it's just using a weighing scale, but for a manipulator, you'll have to do some movements, and then there's something called, there's a whole area of research called system dynamics, so system identification, which talks about how to figure out mass, damping, and so on. And that is, we'll not actually do that, but these numbers which will come out from that are just estimates. Sometimes when we do very careful system identification, we'll actually figure out the exact m, which is a nice thing to have, because now control becomes easy because you have perfect models. So in a simulation world, you have perfect knowledge of the mass c and g. So what we'll do is we'll assume why don't okay, let me keep it in this form of mass hat, and then make the assumption that the mass hat, m hat, is same as m, and so on. So let's put this equation 2 in 1, so we have mq double dot plus cq dot plus gq equals m hat minus kpq minus kdq dot plus c hat q dot plus g hat q. So what you can do is you can take these terms to the left side, and also this one to the left side, and you get So C minus C hat Q dot plus G minus G hat Q plus MQ double dot. So this is, I've only taken these terms to the left side. So I have this, and then this I keep as it is. And then what I'll have to do is I'll have to invert this n. So multiply both sides by m hat inverse. And so I would have m hat inverse multiplying this whole thing. Let me move it to the left. Okay, and then these terms will show up on the left side. K PQ plus KDQ dot equal to 0. Okay, so again, I first move these terms to the left side, so I get that term as it is, and then this will remain on the right side. I need to multiply both sides by the inverse. So that way, m hat inverse multiplied with m gives me 1. So I have the inverse coming up in front of this term, and then the KP, KD just moves to the left. So that's my equation. What I'm going to do is, now I'm going to assume we have perfect model, which means that I know what m hat is, it's just equal to the mass. And I know what c hat is, it's just equal to c. And I know what g is, it's equal to g hat. So if I do that, then I get m hat inverse, so m inverse, because m hat is m q double dot plus c minus c q dot plus g minus g q plus kp q plus kd q dot equals 0. So clearly this term is 0, this term is 0. When you multiply m inverse with m, you get 1 identity. So this equation boils down to q double dot plus kp q plus kdq dot equals 0. Well, let me write this as q double dot plus kdq dot first plus kpq equals 0. Okay, so we took a system which looked pretty involved. It involved mass, centripetal term, and gravity, and reduced it to this system, which now is quite simple, because this is actually say n degrees of freedom, but all these equations, the n degrees of freedom, are independent. They do not depend on each other, which means that you can think of this as n equations, each of them represented by this one, and they do not talk with each other. So controlling one doesn't affect the other one. So now what we do is now use the same trick we did in the previous last part of last class. So I wrote down this formula for KD as a function of C and M. This is for a 1 degree of freedom system where M is the mass, C is the damping. So let me copy that first. So recap, for a system which looked like this, mq double dot plus k kd, sorry, c plus kd q dot plus k plus kp q equals 0, lecture 17. So for this system, which is after input torque equals the PD controller, we found that to have critical damping, we need this damping term, right? So now we can look at this equation and try to use that to find a controller, the values of Kp and Kd, so that this system is critically damped. So comparing one with 2, we see that the mass for this one is 1, C is 0, K is 0. So our Kd is simply minus C, which is 0, plus 2 square root mass, which is 1, K is 0, plus Kp, which is Kp. So to control the system to be critically damped, that's the choice we need to make. It's much simpler. System to be critically damped. Okay, so now the system is critically damped, provided you choose Kd equals 2 square root Kp, and also you need to choose torque. Is that you need to choose the torque like this, in this fashion, right? Provided you choose torque in this fashion, where Kp and Kd relation is found, you will get the system to be critically damped. In fact, it's much simpler. It's basically writing n equations. Each of them are independent of each other. Okay, so this is when I saw this first, it's really hard to understand, but you should read this once or twice and you'll get the gist of it. It's really playing with the math, and more than anything else, there is no there is a physical meaning to how it's done, but you want to repeat this yourself to understand the math. So again, we can draw a block diagram for that system. I'm going to attempt to draw the block diagram. And then I'll show you a simulation of a 2 degree of freedom system based on the math. So again, the equation of the system is mq double dot plus cq dot plus kq equals torque. Torque formula was m hat minus kpq minus kdq dot plus c hat q dot plus g hat q. And so this is how, as always, start off with the system dynamics, cq dot plus kq. Okay, since there's feedback on the position and velocity, my outputs would be q and q dot. Okay, now those outputs will go to another block because there's a c hat q dot term plus g times g hat c hat q dot plus g hat q. So those are fed. C and q are found out because there are constants and they are functions of q. What I did not write is c is actually q dot. So it's a function of q dot. So unless you have q dot, you cannot find c. Also, it has some constant terms, and g is actually g of q. So you need q. So basically, this block takes in inputs as q dot and q, finds c hat q and g hat. We also have to feed this term. So move on. Multiply this with, since this is q, I multiply this with kp, and then there's kd. So q is fed here, q dot comes from that. Okay, what else do I need? Okay, so this is fed with negative feedback. Okay, I also need to multiply, so this will give me minus k, not here, this will just be k d q dot k p q. This, what comes out of here has to be, is basically this term after it is summed, and then I have to multiply that with the m hat term. So m hat would appear here. Okay, and then I need to sum this also. So there'll be another block running out of space. Let me clean this up. Okay, so this is fed to a summing block. M is also fed to the summing block. What comes out from here is the torque. The torque is now going to be this formula. So you can check it out. So torque it's going to be m times whatever comes here, or what comes here is kd times q dot, kp times q. So you sum them up and you multiply with m, and then you sum that up with the right side, which is this part, and that comes out v dot, and that's fed to the system. So it's a bit complicated, but that's how it is. So what this controller does is it actually tries to control the system to go back to zero, just like the spring mass tamper. So most times we are not interested in going to zero. A manipulator has to track a trajectory. So we talked about trajectory generation. Given start, given a goal, we have the minimum, what do you call it? Starts with zero velocity, zero acceleration, goes to zero velocity, zero acceleration, two different endpoints. We drew this, the time trajectory based on fitting a polynomial. So that's the trajectory we want to track. And so typically we don't want to go to zero, but we want to be able to track the trajectory. So if you want to do trajectory tracking, this is known as, by the way, set point control. This is, in fact, it is set point control. Okay, where the set point is just zero. Why is it zero? It's because of this term. You have minus kp q minus 0 minus kd q dot. When you have something like this is the set point, right? This is the same thing as what you did for your line following robot. You have the set point. In this case, it will be the intensity of the black, and you try to achieve that. Some of you did that, not all of you did PD control. But most times we are interested in what is known as the trajectory tracking controller. Trajectory tracking. What's trajectory tracking? You could have a trajectory like this. This is QD as a function of time. So we want a manipulator. So this is, say, one joint, and that joint has to follow that profile. And so you need to modify your torque to be able to track that. So this is track this trajectory. So this is for one joint, as I said. For your n joints, you will have n different trajectories. Some of them could actually be just staying zero. Some of them could be tracking. But the way you do this tracking is you modify your controller It's a very slight modification. You just change the set point qd minus kd q minus qd dot minus plus plus c hat q dot plus g hat. So this is the modification. Set point is a function of time. Okay, and you're also setting the velocity. It's a mistake here. It should be q dot. This should be q dot q dot. So you know q, so you know q dot, and you can track a trajectory this way. So an exercise is draw the block diagram for this controller. Okay, so let's do some simulation with a 2 degree of freedom system. I'm going to start off with a system which has no meaning. It's basically a system where I cooked up the mass and then we'll do a pendulum. Go from there. Okay, so this is cooked up example where the mass matrix, so it's no longer 1 degree of freedom, it's 2 degree of freedom because the mass matrix has 2 rows, 2 columns. So 1.1.12. C also has, in this case I chose it to be diagonal. Maybe this will make it easier to understand. This is how the system looks. Then and so on. So again, what you do is okay, I actually have a case where there's an imperfect model. I modified the mass matrix by making an m hat, so our estimate is bad, and then the estimate is good. But let me do one thing first. Let me just get rid of this. And I do need this. Okay, so there are just 2 files here. There's no animation because it's just a cooked up example. There is the main file and then there's the right hand side file. This is where the torque will appear, and you can see that the torque formula has, it's exactly what I wrote down. Okay, where our goal here is to choose, after we chose the form for torque, we just have to choose a form for the Kp and Kd, which are right there, and I've that in the main file. But you can see in this case there's a set point qd, so I modified that equation. It's not 0 set point, but there's a certain reference set point. So let's see what I have for the set point. So I want the first degree of freedom to go to 0.5, second one to go to 0.1. Let me just do this. just a single plot. So the single plot shows I start from 0, 0. So think of this as two spring mass dampers, each of them starting at 0, but I want the spring mass damper, the first one to go to 0.5, and the second one I need to go to 0.1. And so this is how the response looks. So you can see that it's critically damped, there's no overshoot, and apparently this is the shortest time. So if you try to play with the KP/KD, you'll see that you will not get any time which is faster than that for that particular KD. So what I did was I chose some KP, and then KD is 2 square root KP. That's the same formula I wrote down. Now, if you want to do it much faster, just say figure 1. So you can see that it takes about 4.5, almost 6 seconds to get to 0.1. That one's a little faster, but we can just use this as a reference. 0.6 seconds. What I'm going to do is I'm going to ramp up my KP. I'm going to make it 10 instead of 1, and redo this. And now you can see that it's reduced from 4.5 seconds to 1 second, less than 1 second. That's because the KP has been increased, ramped up, and so again critically damped. So your KP determines the rate of response, and KD determines the damping, whether it's going to oscillate or not oscillate. So it's 100 times now. At some point it will actually break. It will be unstable because of the integration. So it's much faster. It's going faster. You can also introduce, as I said, we assume that our model was perfect, but what if our model was not perfect? This is, I introduced m hat, which is the mass plus some error term. So we are not perfect in estimation of the mass C and K. If I run this, I'm not sure what it's going to produce. Yeah, so it goes off. That's for one. Let's try. Slightly better. There's an error. You can see there's a steady state error. Steady state error is when the set point is not met. So here's a problem where the system identification was not perfect, and so we had to play with the gain so that the system can be controlled. Let's ramp this up to 100, and maybe it will be perfect tracking. Okay, now you get it's good tracking. So this is a case where you have a bad model for the system, and you compensate for the model by using a high gain feedback controller. I had to put 100 for the KP to make the system track the